Okay, I'm back. We're now going to do part 2 of the section 4.2 lesson. And here we're on the second page, example 1. We finished parts A and B. Let's take a look at part C. You have to find the equation of the secant line AB if A and B are endpoints of the function. So that one shouldn't be too bad. I'm actually going to do part C up here because I don't have terribly much space. So we know that point A was 0, 1. And part B was, if we call this A, we'll call this B, and we're going to find the equation of this red line right here. Well, the slope we already know, because we did that actually in part B when we did the average rate of change. So again, our point B is 1, 0. Oh, hold on a sec. Ah, geez, I totally messed this up. All right, let me erase this. Point A is supposed to be negative 1, pi. There we go. If you knew I made a mistake, that's good. I was looking at the cosine function. I have to look at the inverse cosine function. And point B is 1, 0. And we know the slope is already negative pi over 2, because that was the average rate of change that we calculated in part B of this problem. So y minus y1 equals m times x minus x1. That's what we use to find the equation of a line. And you can use either one of these 2 points, either A or B. Doesn't matter. If I use, say, point B, you have y minus 0 equals negative pi over 2 x minus 1, or y equals negative pi over 2 times x minus 1. So that would be the equation of the secant line, which makes sense. It looks like it would cross the y-axis at positive pi over 2, because that would be, I guess, our y-intercept, and the slope is negative. So that's part C. Now part D, you're asked to find the equation of the tangent line x equals c and graph it with the secant line and the tangent using the following window that we see right here. And so we'll use this calculator app right here. But before I do that, let's find the equation of the tangent line. So I'll have to tuck it in probably over here somewhere. And let's change colors for a bit of contrast. So again, our slope is going to be negative pi over 2, because remember, our derivative equals our average rate of change. We want to have the same slope. So we're still going to use the same slope. And we're going to do this for 2 points, right? Because, notice we said equations. One of our x coordinates was 0.771. Remember, that's what we did in part B when we solved for C. That was the end of part 1 of the video. If you find the y coordinate goes with that, you want to plug it back into inverse cosine of x, which is our original function. And that would be 0.690. You do want to get in a habit of rounding your decimals to 3 decimal places. And then negative 0.771, comma 2.451, if you were to work that out. And actually what I am going to do, just to be a bit more precise with my answers, is that I'm going to store 0.771 and negative 0.771 in my calculator. So remember, we got that when we did 1 minus 4 over pi squared. Oh, oops. I was supposed to square it as well. Square root. There we go. So let's say store that as alpha c. You might want to do this in your calculator as well. Now we could also do negative 0.771, because remember it was plus or minus, but we could just store 0.771 as c, then do negative c if we have to do the negative counterpart. And then remember, we want to do inverse cosine of alpha c. That's when your x coordinate is 0.771. which is 0.690. I'll store that as alpha d. And also just ensure that I'm in radian mode. I am, that's good. And then inverse cosine. Now let's do negative c. 2.451. Store that as alpha e. Okay, so we're going to do this so that our graphs are precise. But to get the tangent lines, pretty easy. First tangent line would be y minus 0.690 equals negative pi over 2 x minus 0.771. And of course, y minus 2.451 equals negative pi over 2 x plus 0.771. So those are your equations of tangent lines. Now we're going to graph this with the secant line. And we'll even do the original function too. So I'm going to go to y equals. I'm going to clear all the stuff here. Looks like that was from a previous video. It's the only time I really use this app. You know, wouldn't hurt to use it more often. So inverse cosine of x, that's the original function. Remember the tangent, the secant line is here in green. So negative pi divided by 2. That's not good. Negative pi divided by 2 x minus 1. And then, of course, the other ones. Now, the way I'm going to write the first one here in red, negative y minus 0.690 equals negative pi over 2 x minus 0.771, because I stored this is d, this is e, and that is c, I could just say alpha d minus pi over 2, because I'm just moving 0.690 over, and x minus c. I think that is correct. Yes, that's what I want to do. And then, of course, then next one will be alpha e minus pi over 2 x, in this case plus c. Hopefully I'm going slow enough so you guys can follow. If I had a real calculator, you could see my exceptional calculator entry skills. Let's go to window, and let's make sure our window is appropriate for this graph. So we're going to go from negative 1.175 to positive 1.175. And from 0 to 3.16, because you remember that's pi, we went from 0 to pi for y and negative 1 to 1 for x. And we kind of want to see what's going on. We don't want the window too tight, so kind of want to see what's going on to the left and the right. So there's the inverse cosine function graph coming. Then the secant line is right there, and then the tangent lines are coming. And notice how those tangent lines are parallel to the secant line. And so we see MVT in action, which is really kind of cool because we see there's at least one tangent line that is parallel to the secant line. In fact, we have two. Or the fact that we have at least one derivative value that's equivalent to the average rate of change. So we saw MVT in practice here, which is kind of cool. Okay, let's look at example 2. Now these are a bit more, you just have to think about these for a bit more, I don't say qualitative, but you kind of have, not too much math issues, you just have to think about these. So let's go back to Mr. Reyes. He was driving continuously 130 miles in 2 hours, and his Ferrari starting from rest. Will there necessarily be at least one instance when its speedometer will be 65 miles per hour and 40 miles per hour? Well, we're going to say yes to both of these, and I'll explain to you why. For part A, remember his average velocity was 65 miles per hour, right? 130 miles, 2 hours, divide the 2, that's your average velocity. Well, according to MVT, there's at least one time in our interval from 0 to 2 hours when the instantaneous rate of change, which is the derivative, right, equals average rate of change. Or graphically, the slope of the tangent line equals the slope of the secant line. So MVT says that. We would think that this would be a continuous function, differentiable at every point within our interval. So that's the deal there. Now for part B, this is actually according to IVT. Now if you forgot IVT, this is from the section 2.3 notes, last page, I think page 5. I'm going to try to see if I can expand this without ruining the ink. Yeah, I kind of just ruined it. Let me just undo that. But basically it says that if a function is continuous on a closed interval, it will take on every value between f of a and f of b at least once, if your interval goes from a to b. So if you have a as one left endpoint, b as a right endpoint, and the function is continuous between a and b, there's going to be a value in between a and b such that the y value will also be between the y values for a and b. So you'll have at least one value between f of a and f of b in your interval. That's what we call intermediate value theorem. So to restate that, at least one time in our interval, and let's say we go from 0 to t1, when your velocity is 4 miles per hour. And if we say the velocity at 0 is 0, and the velocity at t1 is 65, because we do know he's going to hit at least 65 miles per hour, right? Then, and if we draw, try to draw a quick graph, like maybe look something kind of like this. Here's t1, here's 65, and here's 0. Of course, we hit 40 somewhere in the middle, according to IVT, as long as we have a continuous function. So that's what happens with that one. Some other things we need to talk about. And this is kind of the real importance of mean value theorem, and it kind of leads to 4.3 really nicely. So we talk about MVT corollary 1. So given that function f is continuous on a to b, where a and b are included, and differentiable on the interior of a and b, then we could say that our derivative is going to be greater than 0 or positive at each point a and b if our graph is increasing on that interval. So let's look down below. Notice how that's a, and of course that's b, right? And the graph is increasing. If you drew tangent lines, all these tangent lines are positive. That would imply that your derivative is positive. So whenever your graph is increasing, between 2 points, our derivative is going to be positive. Or I guess another way of saying it, if our derivative is positive from a to b, the graph is increasing. Likewise, if your derivative is negative, then your graph will be decreasing. Notice how this is a decreasing graph. Again, here's a, here's b. If I drew all these different tangent lines, they all have negative slopes. That would be a negative derivative. So, and make sure you do pay careful attention to the brackets and the parentheses. The brackets, we're including a and b because f is increasing because a and b are part of our domain. But remember, it's not going to be differentiable at the endpoints. So as long as the derivative is greater than 0 on the interior of a and b, then f is increasing on the interval from a to b with a and b included, and same thing with the derivative when it's less than 0. So another way of looking at it is that if your function increases on the interval, and if x1, here's x1, is less than x2, then we know f of x1 is less than f of x2 because it's increasing, right? And if on your interval, again, x1 is less than x2, here's x1, here's x2. But if f of x1 is greater than f of x2, that means the graph is decreasing, right? Because y values are going down. So again, here, f increases on a to b. Here, f decreases on A to B, where that's x1 and that's x2. Okay, let's look at examples 3 and 4, and then I'll take another break from the video because I don't want you guys get too overwhelmed with all this video watching. Definitely want to take some breaks. That's not good. There's a little bit of an overlap there. That's okay. I'll fix it later. Let me just expand this a bit more. So we'll conclude page 4 here for part 2 of the video. So here we're asked to determine the intervals where the function is increasing and decreasing. Well, now we've kind of made this connection with the derivative. When the derivative is positive, the graph is increasing, derivative negative, it's decreasing. So let's find the derivative. Real easy. Derivative is going to be 3x squared minus 3. So we want 3x squared minus 3 to be greater than 0, and 3x squared minus 3 to be less than 0. If it's greater than 0, we're going to have this happening, and we're going to have to factor it. Remember doing sign charts and doing this in pre-cal often? That's why I call it pre-cal. We get you ready for calculus, because you got to do this stuff. So I make my sign chart. I locate my zeros, which are also critical points, by the way, because they make the derivative 0. And if I work from right to left, I know that if x is greater than 1, the inequality, or the expression 3 times x minus 1 times x plus 1 is going to be positive. Of course I know that. And if I'm moving from right to left, at x equals 1, all of a sudden, this factor now becomes negative when I'm less than 1. But this stays positive, so I have a negative here, and then it alternates back to being positive. You could plug in values if you wanted to, like plug in 0 between -1 and 1, or plug in -2 to the left of -1. But that gets to be a bit cumbersome. The best thing to do is start from the right side and ask yourself, okay, what's going on there? And move from right to left. And as you pass each of these borders, like this right here, ask yourself which factor is going to be changing sign, or could be changing sign, and how that impacts the overall expression. So we see that's definitely increasing in this interval from -infinity to -1, and from 1 to infinity, because the derivative is positive. Or greater than 0. And it's decreasing in between -1 and 1. And that's because our derivative is negative, or less than 0. So there are your answers. Now there's a more formal way of writing it, which I will write it, and I do ask you guys to do the same. And then we'll do example 4 and wrap up part 2 of this video. So here's a more formal way of writing it. I'll do it in blue. F increases on -infinity to -1, and 1 to infinity, and that should be a bracket. Sorry about that, not very clear there. Because f prime is greater than 0 on the interval -infinity, -1, not inclusive because it's differentiable there, and 1 to infinity. And then f decreases on this interval, -1 to 1, because f prime is less than 0 on -1 to 1, not inclusive for that. That's a more formal way of writing it. So let's try this again for example 4. You might want to pause the video, see if you can figure it out, but I'm going to do it right now. I'll do the derivative down here. F prime x will be 1 times √9 minus x plus x times 1/2 9 minus x and -1/2 times -1. You guys should be pretty comfortable with product rule and chain rule. I did give you guys a packet to work on that over break. For some, and some of you definitely could use some extra practice there. So make sure you guys are comfortable with derivatives, because we do derivatives, like it has to be like the back of our hand now. root 9 minus x plus negative x over 2 root 9 minus x. You're probably going to want to combine these fractions. So f prime x will be root 9 minus x over 1 plus, again, negative x over 2 root 9 minus x. Multiply both top and bottom by 2 root 9 minus x. So you get 2 9 minus x plus negative x over 2 root 9 minus x. That'll be 18 minus 3x. Factor out the 3. You wind up getting this. So that was fun. So that's our derivative. It's 3 times 6 minus x over 2 root 9 minus x. Now, we want that to be positive, so I'm going to rewrite it, so don't worry if you can't see it. I mean, of course, you can always rewind or pause the video. But we want this to be greater than 0. And of course, we want it to be less than 0. So again, we do a sign chart. Here's 6. Here's 9. Now we ignore this part because anything larger than that makes the bottom undefined. And of course, 0 does not exist at 9 as well. It's 0 here. And we would see that the derivative would be positive in this interval and negative in that interval. So we could then say that f prime increases on this interval from negative infinity to 6. 6 is included. I don't know why I didn't do a bracket there. And f prime decreases on the interval from 6 to 9. And remember, 9 is not included because it's not part of our domain, so be careful about that. And the reasons why is because f prime was greater than 0 on negative infinity to 6, 6 not inclusive, and of course f prime was less than 0 from 6 to 9. Okay, so that ends part 2 of the video. There'll be one more part coming, and I'll hopefully do that soon.